Alright, 11.3, Geometric Sequences and Series. In this lesson, we want to learn to write the rules for geometric sequences and find sums of geometric series. Let's begin. First of all, what is a geometric sequence? A geometric sequence is a sequence where the ratio of any term to the previous term is constant. That is, there will be a common ratio. Let's look at an example where you have to determine if it is a geometric sequence. To determine if a sequence is a geometric sequence, what you want to do is take the last term, which in this case in A is a negative 32. You always want to divide by the previous term, which in this case is 16. When we divide negative 32 by 16, we find a ratio of negative 2. Do the same thing with the next term, 16 divided by its previous term. And again, we have a ratio of negative 2. Take the next term, negative 8, and divide it by its previous term. And again, we have a ratio of negative 2. Since there is a constant ratio of negative 2, then we can say in A, yes, we have geometric sequence with a common ratio of negative 2. Let's look at B. First, let's erase, make some room here. So now let's look at part B. Again, we want to take the last term over the previous term. We would get a common ratio of negative 3. Then take the negative 81 over the previous term. And when we divide, we get 3, but notice it's a negative divided by a negative, so we get a positive 3. Negative 3 does not equal positive 3, so for part B, there is no common ratio. It is not a geometric sequence. Okay? So to determine if your sequence is a geometric sequence, you want to check and see if there is a constant ratio. To find that constant ratio, divide your previous term, divide by the previous term. Alright, let's go on to the next example. Before we do our next example, we need to talk about how to write the rule for a geometric sequence. In a geometric sequence, you can write the rule for any term by taking the first term and multiplying it times the rate raised to the power of n minus 1. Remember where n represents the number of term that you're finding, and r is the rate, and the a sub 1, this is your first term. So let's give it a try. In this example, we're asked to do a couple of things. The first thing we're asked to do is to write a rule for the nth term. Because this is a geometric sequence, first thing we want to do is find what the rate is. So we're going to take the last term and divide it by the previous term, 0.32, divided by 0.8, and we find that we get 2/5 or 0.4, whichever way you would like to write it. You might want to continue to check. They didn't necessarily tell you this was a geometric sequence, so you would want to check it out. You could take each term, 0.8 divided by the 2, you're going to find that you again get a 0.4, 2 divided by 5, you again get 0.4. So we know that our rate is 0.4. Now let's write our rule. Any term is equal to the first term, which in this case is 5, times the rate, which is 0.4, raised to the power of n minus 1. So here's our rule for any term. This cannot be simplified any further. A common mistake would be to try to multiply 5 times the 0.4. This cannot be done because they are not being raised to the same power. The understood power on 5 is 1, but on the 0.4 the power keeps changing. 0.4 raised to the power of n minus 1. So you cannot simplify this product. Alright, so now let's find the 8th term. To find the 8th term, all we need to do is substitute in 8 for the term number. Simplify, so we have 5 times 0.4 raised to the 7th power. Put this in your calculator. Simplify, and you find that this eighth term would be approximately 0.008. I do need to point out at this time that to write your rate as a decimal, this needs to be an exact answer. So if the rate is not an exact answer as a decimal, you may not use a decimal answer. You would need to use the fraction in the rate position. Okay? As long as the decimal answer that you get is an exact decimal answer, then you can write it as a decimal if you'd wish. Okay? But if it's not, then you would need to write that rule using the fraction. So another way that we could have written this rule, we could have said that any term would have been equal to 5 times 2/5 to the n minus 1 power. And you're going to need to do that anytime this rate would not be an exact decimal answer if you were to use the decimal. Okay? So make sure you're using exact answers, not rounded decimal answers. Alright, let's move on. In example 3, you're given the fourth term and you're given the rate. Using the fourth term and the rate, they want you to write the rule for any term. To do this, we take the rule for a geometric sequence. Remember, the rule for a geometric sequence is that any term is equal to the first term times the rate raised to the n minus 1 power. Well, if we knew the first term and the rate, we could write the rule. No problem. Problem is, we've not been given the first term. We've been given the fourth term and the rate. So we plug in the fourth term. Remember, any term, and this is the fourth term, 3, is equal to the first term times the rate. Now we were given the rate. The rate was also 3. Raised to the power of the number of term, well, this is the fourth term minus 1. Simplify then, 3 is equal to the first term times 3 to the third power. Well, 3 to the third power is 27, so 3 is equal to 27 times the first term. Divide both sides by 27. So the first term is equal to 3 divided by 27, or 1/9. Now this is the first term. Now that we have the first term, we can come back and do what we were asked to do, which is write the rule for any term. So plugging the rule for any term into our geometric sequence, we would have any term is equal to that first term times the rate raised to the power of n minus 1. That's it. Remember, you can't simplify this any further because the rate is being raised to a power. This is as far as you can go. This would be the rule. Alright. Now at this point, I'd like for you to pause the video, try to work checkpoint 1. After you unpause the video, I will give you the answers. I'd like for you to check your answers, and if there's any problems, go back, watch maybe example 2 again, and see if you can figure out what your situation is, why you're not getting the correct answer. Alright. You should have, if you've solved this correctly, you should have found that your first term, before beginning this problem, to begin this problem, you should have found that the first term was a negative 2/9. Then using that first term, you could write your rule for any term, which is part of what you were asked to do in this problem. The rule for any term you should have found was negative 2/9 times the common ratio, 3 raised to the n minus 1 power. So there was the rule that you should have written. And then after you've done that, the last thing that you were asked to do was to find the eighth term. You should have found that the eighth term was equal to a negative 486. If you had any problems with this checkpoint, maybe go back and watch example 3 again. And otherwise, you can ask me questions in class tomorrow. Alright, let's move on to example 4. Example 4 is just a little bit different. They've given us two terms. They've given us the second term and the sixth term. And they're asking us to write a rule for any term. Just like we did with arithmetic sequences, we're going to need to write a system of equations. We're going to write a system of equations using what we know about geometric sequences. Remember, in a geometric sequence, any term is equal to the first term times the rate raised to the n minus 1 power. The problem is we don't know the first term or the rate. All we know is that the second term is a negative 4 and that the sixth term is a negative 1024. So we'll use those two terms to write a system of equations. So the second term, which is a negative 4, would have been equal to the first term times the rate raised to the n minus 1 power. Now we know what n is. N, because this is the second term, n is 2. What we want is n minus 1, or 2 minus 1. 2 minus 1 then would make the power here of 1. I want to do the same thing with the sixth term. The sixth term is a negative 1024. That sixth term would be equal to the first term times the rate raised to the n minus 1 power. Remember, n is the number of term. Well, this is the sixth term. We want n minus 1, or 6 minus 1, which would be 5. So we have our system of equations. Now we need to solve. The easiest way to solve this system of equations is to use substitution. It would be easier to rewrite this equation, divide by the rate. So the first term would be equal to negative 4 divided by, since it's r to the first power, we can just say divided by r. Now, we're going to use substitution, so we're going to take this and substitute it into our second equation where a is at. We're going to substitute it in here for a. So we'd have negative 1024 is equal to that first term. For that first term, we're going to substitute in negative 4 over r. Because remember, when we rewrote our equation here, the first term was equal to negative 4 over r. So we're substituting that in for the first term. Alright, let's finish writing the equation. It's that first term times r to the 5th power. Well, now we want to simplify. When we multiply negative 4 over r times r to the 5th, remember, we can do some canceling here. We would be able to cancel the r, this r to the 1st with the r to the 5th, and now r to the 5th would become a 4th power. So we end up with negative 1024 is equal to negative 4 times r to the 4th power. Remember, when you're dividing exponents, what you really do is subtract. Okay? So that's what we did here. That's how we ended up with the 4th power. Alright, now to simplify, divide both sides by 4. You divide both sides by 4. A negative divided by a negative would be a positive, so we're going to end up with a positive 256 will be equal to r to the 4th power. Then we would take the 4th root of both sides, so r would be equal to the positive and negative. Remember, when it's an even root, it's both positive and negative. 4th root of 256. Well, the 4th root of 256 is 4, so we would end up with a rate of positive and negative 4. Since there are two possible rates, then we would have two possible first terms. Now, to find what the first terms are, you want to take these possible rates and put them back in where you had rewrote the first term. Then the first term, remember, is equal to negative 4 divided by the rate. Well, then the first term could possibly be when the rate is a positive 4, the first term would be a negative 1. When the first term, when the rate is a negative 4 divided by negative 4, you would end up with a positive 1. Since there are two possible rates and two possible first terms, we have two different possible geometric sequences that would both give us a second and sixth term, like they've given us a second term of negative 4 and a sixth term of negative 1024. So we need to write both rules. Alright, so the rule for any term. The rule for any term, remember, is equal to the first term. Well, one possible first term was negative 1. Times the times the rate. Now, we got a negative 1 when the rate was a positive 4. Raised to the power of n minus 1. This would be one rule. Or, the rule could be any term is equal to, the other first term was a positive 1, and we got a positive 1 for the first term when the rate was a negative 4. Raised to the power of n minus 1. Alright, so there were two possible solutions to this, two possible rules that would give us a second term of negative 4 and a sixth term of negative 1024. If you want to verify that these rules are correct, you could do a table of values for each one. Let's clear this up a little bit so we have some room to write. Okay, let's do a table of values for the rule where any term is equal to negative 1 times 4 to the n minus 1 power. And let's do from the first term to the sixth term. Now, using your calculators, this would be quick. When you punch this into your calculators, using the table value, the first term would be a 1. The second term would be a negative 4. The third term would be positive 16. The fourth term would be a negative 64. The fifth term would be a positive 256. And the sixth term we would get a negative 1024. So we see with this rule that it worked, that we did get for the second term a negative 4, and for the sixth term a negative 1024. Let's take the other rule. The rule that said that any term would be equal to positive 1 times negative 4 to the n minus 1 power. Again, using the calculators and doing a table of values, let's again go from the first term to the sixth term. The first term you would get a negative 1, the second term a negative 4, the third term a negative 16, the fourth term a negative 64, the fifth term a negative 256, and the sixth term, again, a negative 1024. So we see this rule also fits what we were given, that the second term was a negative 4, and that the sixth term was a negative 1024. So we find that these two are correct solutions. The rule here would be, there would be two rules. Any term could be equal to negative 1 times 4 to the n minus 1 power, or any term would be equal to 1 times negative 4 raised to the n minus 1 power. Alright, pause the video, give this checkpoint exercise a try. If after unpausing the video and checking your answers, you find that you have not gotten the correct answer, maybe go back and watch example 4 again and give it a try again. Alright, the system of equations that you should have written for these would have been negative 18 is equal to the first term times r raised to the power of 1, and then 2/3 is equal to the first term raised to the power of 4. You should have then solved and found that the first term was 54 and that the rate was a negative 1/3. Then plug those in and found that any term would be equal to that first term of 54 times the rate of negative 1/3 raised to the power of n minus 1. Okay, now I've just given you the answers here, not shown you how to solve it. If you had problems solving it and getting these answers, go back, watch the previous example, try it again. If you're still having trouble, see me in class tomorrow. Alright, let's talk about a geometric series. Remember, a series is a sum of a sequence. So the expression formed by adding the terms of a geometric sequence is called a geometric series. The rule for a geometric series is that the sum is found by multiplying the first term times the quotient of 1 minus the rate raised to the power of n over 1 minus the rate. So what you need is the first term, you'll need the rate, and you'll need to know the number of term to find the sums. So let's give it a try. In example 5, we're told that this is a geometric series. So we know we want to use the rule that we just discussed, where the sum can be found by multiplying the first term times 1 minus the rate raised to the nth power over 1 minus the rate. So we first need to know what is the first term and what is the rate. Well, the first term, that's easy. The first term is a 4. To get the rate, remember, divide by the previous term. You could take 1/2 and divide it by 1, which would give you a rate of 1/2. You could go 1 divided by the previous term, 2. 1 divided by 2 still gives you the rate of 1/2. 2 divided by the previous term, 4, you still get the rate 1/2. So we know our rate is 1/2. We have our first term. Our first term is 4. We're ready to write our rule for any term. So the rule for any term would be equal to the first term, which is 4, times 1 minus the rate to the nth power over 1 minus the rate. I forgot to put the rate in. Rate was 1/2. I want you to put 1/2 in the top also. Come back and put the 1/2 in. Alright. Now, in the denominator, we could go ahead and simplify the 1 minus 1/2. We want to find the sum of the first 10 terms. So we can go ahead and put n in. We got 4 times 1 minus 1/2 raised to the 10th power. Okay, so we cannot, in the numerator, we cannot subtract the 1 minus 1/2 because we need 1 minus 1/2 that's been raised to the 10th power. But in the denominator, you could go ahead and do 1 minus 1/2 and end up with a negative 1/2. At this point, because we use calculators in this class, you could just go ahead and punch this into your calculator just as it appears here on the screen. Once you've punched this into the calculator, you should end up with that the sum of 10 terms is equal to 7.99. Alright, let's move to part B. In part B, it wants us to find n such that the sum would be equal to 31 over 4. So let's set this problem up. So we know that the sum is 31 over 4. That sum would be equal to the first term, which we know is 4, times 1 minus the rate, which we know is 1/2, raised to the power of the number of terms that we are adding, which we do not know. That's what we're being asked to find, over 1 minus the rate, or 1 minus 1/2, which would be a negative 1/2. Now we want to simplify. We want to get rid of the multiplying by 4. Remember, to get rid of multiplying by 4, what we want to do is divide by 4 on both sides. So we divide by 4 and cancel this out. But if we divide by 4 on that side, we need to divide by 4 on the other side. Since this is a fraction, though, when we divide a fraction, that's the same as multiplying by the reciprocal. So we're going to multiply by 1/4. So on our left-hand side, we would end up with 31 over 16 is equal to 1 minus 1/2 to the nth power over the negative 1/2. Now we want to get rid of that dividing by negative 1/2. To get rid of the dividing by negative 1/2, I'm sorry, that's not a negative 1/2, that's a positive 1/2. It was also a positive 1/2 over here in our previous example. I'm sorry if I confused you. Alright, so to get rid of that positive 1/2, we want to multiply by 1/2 on both sides. Multiplying by 1/2 on both sides, let's change the color here so it's easier to see what we're doing. We're going to multiply by 1/2, so multiplying by 1/2 cancels out the dividing by 1/2. Multiply this side by 1/2. We end up with 31 over 32 would be equal to 1 minus 1/2 to the nth power. Then we would subtract 1 from both sides. So we want 31 over 32 minus 1, okay, or 31 over 32 minus 32 over 32 would leave you with a negative 1 over 32. Is equal to a negative 1/2 raised to the nth power. Alright, now at this point we need to remember how to solve exponential equations. Remember, to get rid of a base of 1/2, we need a log with a base 1/2, but we can't use negatives, so we need to get rid of the negative. We can divide both sides by a negative. That would make both sides become positive. Okay, and so then we want to use the log base 1/2 to cancel out the base 1/2. So we'll do a log with a base of 1/2, which cancels out the base 1/2. But then we also have to do that on the other side. Log base 1/2 of the 1 over 32. Okay. Now this can be punched into your calculator using your any log button. Now that's just a positive 132 right here. 1 over 32. Punch it into your calculators then. Log with a base of 1/2 of 1 over 32 and get your solution. If you punch this into your calculator correctly, you should have found that n was equal to, not approximately equal to, exactly equal to, because we're looking for the number of terms, exactly equal to 5. Alright, so the fifth term would give us a sum of 31 over 4. Alright, at this point, I would like for you to pause the video and try to work checkpoint exercise here. Okay, so I'm not going to show you the work for this checkpoint. I'd like for you to try. Alright, if you worked it correctly, you should have found the sum of the first 5 terms would be equal to a negative 1,220 over 27. Okay, that's the sum of the first 5 terms. Alright, and then they asked you to find the number of terms that would give you the sum of negative 32,800 over 729. You should have found that that would take 8 terms. the sum of the first 8 terms would be negative 32,800 over 729. If you had problems with this, you can see me tomorrow. Alright, let's move on to example 6. You buy a new car for $25,000. The value of the car decreases by 16% each year. Okay. So we want to write a rule for the average yearly value of the car. So in a year, the value of the car would be equal to the original $25,000 that we started with, times the rate. Well, now rate is decreasing, so it would be 1 minus the 0.16, a rate of decrease, raised to the power of n minus 1. So we have to find what our rate of decrease is here. So the rate of decrease, 1 minus the 0.16, then if it's decreasing by 16%, then the value that remains would be 84%, raised to the power of n minus 1. Okay? So this would be the rule for any term. The value at the end of any year could be found by taking the original value, 25,000. Now remember, it's decreasing by 16%, so the value that remains is 84%, raised to the power of n minus 1. Here's the rule for any term. Then, in part B, they asked us what would be the value of the car, or in about how many years would the value of the car fall to $10,455. So we want to take that $10,455 and set it equal to our rule, and find out when the value of the car would drop to $10,455. In what number of years? So the first thing you want to do is divide both sides by 25,000. 10,455 divided by the 25,000. Our calculator will leave that as a fraction for us. We would have 2,091 over 5,000. I'm going to keep that exact answer. It would be equal to the 0.84 raised to the n minus 1 power. Now we want to get rid of the base 0.84. So remember, to get rid of a base you need to use a log. So we're going to use log with a base of 0.84 of 2,091 over 5,000 would be equal to, when you do that on the other side, it will cancel out the base and you'll be just left with the n minus 1. Punch this into your calculator. The log with a base of 0.84 of the quantity of 2,091 divided by the 5,000. Once you punch that into your calculator, you're going to come out with 5.0002 is equal to the n minus 1. So it's safe to say that that would be a 5. You have a minus 1, so you want to get rid of that. You add 1. So it would be approximately 6 years when the value of the car would drop to the 10,455. Alright, let's try one more of these word problems. Suppose you have a computer system that loses 1/5 of its value at the end of the first year. At the end of the second year, it loses 1/5 of the remaining 4/5 of its value, and so on. If you paid $2,700 for the computer, what is its average value at the end of each year during the 5 years you own it? So what we need is a rule for any term. Mirror rule for any term. would be equal to the initial amount, the first term, times the rate. Now we need a rate of decrease. The rate of decrease is always found by 1 minus the rate. So 1 minus the 1/5, our rate would be 1 minus the 1/5, or 4/5. Raised to the n minus 1 power. If we now do a table of values using our rule for the first 5 years, we'll see that we have a problem with our rule. Because if we put 1 in for the first year, it makes the value at the end of the first year $2,700, exactly what we started with. But it said that we lost 1/5 of the value at the end of the first year. So we need this first term to represent the value at the end of the first year. To get this to represent the value at the end of the first year, then the amount that we should have started here would have been 1/5 of the, we needed to find out what 1/5 of the loss was. Instead, the first term should have been 2,700 minus 1/5 of 2,700. That's what we would have at the end of the first year. So at the end of the first year, we would only have $2,160 would be the value. So we need to correct that in our formula. At the end of the first year, our first term is $2,160. Now, using the correct first term, we could do a table of values for the first 5 years. Using our calculator, we could put the formula in, and we would find that at the end of the first year, we have $2,160. The value at the end of 2 years, $1,728. The value at the end of 3 years, $1,382.40. The value at the end of 4 years, $1,105.92. And the value at the end of 5 years, $884.74. If what we're wanting to know is what's the average value over the 5-year period, we could have just found the sum over the 5-year period. The sum over the 5-year period, remember, would have been equal to that first term, which is 2,160, times 1 minus the rate, raised to the power of time, over 1 minus the rate. Simplify this using your calculator. You will find the sum at the end of 5 years was $7,261.06. If you divide this by the 5 years so that you get the average value, this was the sum of all of the values after 5 years. Divide it by 5 years to find the average value over the 5 years. The average value over the 5 years then would be $1,452. You could also have found that by adding up all these values and dividing by 5, still would have given you the average value of $1,452. All right, one last problem for you to look at. I'd like for you to pause the video for just a minute and try working this last example. All right, pause the video give this multiple choice problem a try. After you've solved it, unpause the video and check your answer. Okay, if you solved it correctly, you should have found that D was the correct answer. The rule for any term would have been 1.5 times 4 raised to the n minus 1 power. Alright, one more thing before we end this video, and that is to review all of the rules. Let's compare arithmetic sequence to a geometric sequence. In an arithmetic sequence, remember there is a common difference. In a geometric sequence, there's a common ratio. Okay. To write the rule for any number of terms in an arithmetic sequence, remember any term can be found by taking the first term and adding n minus 1 times the common difference. In a geometric sequence, we write the rule for any term by taking the first term and multiplying it times the rate raised to the power of n minus 1. Let's talk about the sum. In an arithmetic, if we want to find the sum, of any number of terms is found by multiplying the number of terms times the average of the first and last term. But in a geometric, the sum is found by taking the first term, multiplying it times 1 minus the rate to the nth power over 1 minus the rate. Alright, there you have a comparison of arithmetic sequence and geometric sequence.